Hi everybody, this is Dr. Momin. This is our third presentation for week 3. Chapter 3 is the topic. The discussion here will be about the counting techniques. Um, Computer science, statistics and probability all involve counting techniques, which is a branch of mathematics. We will introduce in this topic, in this section, uh, different rules of counting and different techniques. The first rule I'm going to introduce would be, it's called the sum rule. And it has to do when you have a selection from different topics or from different items that are you picking only, say, one from a box, one item from a box that has, let's say, two different types, type A and type B. So you have to select one, and what you do in here, you look at could it be from type 1 or could it be from type 2? So you add how many in type 1 and how many in type 2, and so the number of possibilities will be uh, how many in task 1, which is selecting from type 1, or from type 2, and so you add T1 plus T2. To put it in general in here, suppose we have a task that can be completed by performing exactly one task from a collection of disjoint subtasks. Um, Now, suppose each subtask has a choice of ways to perform that selection. Um, we say in here that the number of ways to perform the task is T1 plus T2 plus Tn if we have n different items. Um, the sum rule as an example in here, say you have 5 novels, 4 magazines, and 3 books. When you are sitting into a doctor office waiting to be called, how many options do you have for taking one? Uh, you have 3 subtasks. Pick a novel, pick a magazine, or pick a book. The first can be done in 5 ways, the second can be in 4 ways, and the third in 3 ways. So you have 5 plus 4 plus 3 choices in here, and this is how many ways you can perform that, picking up one item from those 12. And another example in here, suppose we have to select one person from either a computer faculty, a computer science faculty, or a computer science student. So we add how many students plus how many faculty, and then we add them. This is how many ways that we can select. The second rule we're going to introduce in here, which is called the multiplication rule or the product rule. And so this is like a sequence. We do task number 1 first. We select, say, one item, and then next task will be select another item, and task number 3 we select another item, and we continue this way. The tasks consist of a sequence of n steps. There be task 1 can be done in T1 ways. Task number 2 can be done in T2 ways, and so on. So the number of possible ways of completing that selection of the n sequences will be multiplying T1 times T2 times T3 up to times Tn. As an example in here for the multiplication or the product rule, let's say how many ways can we choose 4 colors and paint 3 rooms. Now we don't assume in here that we can have different colors in the different rooms. So all the rooms can have the same color, or some rooms have one color and another one have another color, and so on. So we can have repetitions and so on. So let's say we paint one room with possibilities of 4 colors. So we have 4 possible colors to paint the first room. And then we move to the second room and we paint it with 4 colors. And we move the possibilities, of course, of different 1 color out of the 4. And then the third room will have exactly 1 color out of the 4 colors. So the number of possible ways of painting these 3 rooms will be 4 times 4 times 4. Now, this one allows you to have all the 3 rooms have the same color, or the first room can be different color from the second room, from the third room, and so on. You can have 2 rooms that have the same color and the third room has this one in here. And then the order also here matters. Means that the first room is the first color and the second room has another color, or the first room has the second color and the second room has the first color, and so on. Now let's look into this. If we do add some more condition in here, how many different ways can we choose from 4 colors and paint through rooms if no room is to be the same color as the other ones that has painted? So we come over here and we say we paint one room, we select any room, and we have 4 choices of colors. Now, since we wanted the next room to be different, so we cannot use that color we use. So we have 3 colors left now to paint the second room, and then we exclude that second color, and then we have 2 colors left now to color the second, to paint the third room. So the number of possible tasks in here or different ways would be 4 times 3 times 2, 24 to paint the 3 rooms, but they have different possibility of colors. Now here is another example in here, and in here, of course, what we have in here is that you go into a restaurant and you want them to enter, select a menu from the menu in here, and you have a soup, a salad, a chicken, we have prawns, we have hamburger, we have an ice cream, or we have a pie for dessert. So there are 2 choices for the entries, either a salad or a soup. And then for the main entry, you have 3 choices, and then for the desserts, you have to select one from the 2. So you multiply 2 times 3 times 2. So the number of choices in here will be 2 times 3, and then from each one of those you have a selection of an ice cream or a pie. So 3 times 2 times 2 is equal to 12, and that's what we see in here, the 12 cases of possible ways of selecting what you eat in the restaurant. And we consider it like a tree now. So your first selection, of course, in here you tell that you wanted a soup or a salad, and then with the soup you can check one of those 3, or with the salad you can check one of those 3, and then after that, after you have that selection, then you got to select one of the 2 ice creams. So that is like a tree. So the principle in here is the multiplication and so on. And we look at it again in terms of a tree in here, and here is another example of what we are going to do in the selection. When we buy a PC system, for instance, you have the choices of three models of the basic unit, B1, B2, B3, the two models of a keyword, and so K1 or K2, and the printer, you have this one in here. So again, the number of possible selections in here will be 3 times 2 times 2, the number of choices. Now let's move on to the general rule now is that you multiply n1 times n2 times nk if you have k tasks to be done in a sequence. Now here is another example in here where you are doing a computer program to do a loop, and so the loop has to go with two subscript. Subscript I goes from I equal 1 to 5. Another subscript goes from j for j equal to 1 to 6, and then you perform some kind of a statement. So you start with the I, you select one of the 5 possibilities for I, and then with the j, for each one of the i's possibilities, you select 6 choices, one of the 6 choices of the j. So the number of loops will be 5 times 6 loops. And here is another example in here where the multiplication rule is applied again. You wanted to choose a bin number, and you have a choices between 3 digits repetitions allowed. Since we have 10 digits 0 through 9, and we allow repetitions in here, and the order here matters, so we will have the answer would be 10 times 10 times 10. So that is the possibilities if you have only 3 digits. Let's say that you wanted also to choose a fourth and a fifth digit, but it is a letter. So the letters are 26. So what we have in here, we wanted 5 places. The first 3 are numbers from 0 to 9, and the second, the fourth and the fifth will be letters, and we allow repetitions. So the number of possible bin number would be 10 times 10 times 10 times 26 times 26, which is a huge number in here, which is a 6 million. Excuse me. Yeah, it is equal to 676,000. All right, 676,000 bin possible numbers. And here is another example in here, but we don't allow a repetition in here. So if you fill the first digit, the first place with one of the numbers 0 to 9, so there are 10 possibilities for the first one. Now whatever you select for that one will be excluded, and then the next place will be filled out of 9 digits, and then the third place will be filled out of 8 digits, and then we get to the letters. The first letter is possible to be 26 in the first place, and then the next one would be 25 because we don't repeat the letters. So in this case we'll have 10 times 9 times 8 times 26 times 25, 5 places, but we don't allow a repetition of a number or a letter. All right, now now we're going to talk about permutation and combination. Consider how many ways can we choose R things from a collection of n things. This statement is not very clear. Why? Because do we allow these things to be different, or we allow repetitions? Does the order matters or the order doesn't matter? What does that mean? Means, for instance, let's say, for instance, you're selecting a bin that has 3 possible numbers, and so and we allow no repetitions. So Now the first place could be a 10, and the second place out of the 9, and the third place out of 8. And let's assume that the first number came in to be a 1. And then the 1 will not going to be repeated again in the second place or the third place. But suppose in the second place you have 2, and in the third place you have 4. Now, let's imagine that you have a similar bin number, but with 1 not in the first place but in the second place. So let's say you have 2 and then 1 and then you have 4. Now, is that a different bin number? Yes, it is. So here in this case, the order matters. Having 1 and then 2 and then 4 is different from having 2 and then 1 and then 4. Now, in order to get the general rule for the permutations, and we'll talk about what is a permutation. The permutation is the number of ways of choosing R out of N when we don't allow repetitions, but the order matters. Again, it is how many ways we choose R items out of N, and the order matters. Unlike what we have with the bin number when we're selecting 3 numbers out of 10, and to fill in these 3 places in the bin number. Now, in order to include that rule, we need to include this definition of the factorial. The x factorial, as you know, we call it x factorial, or we use that exclamation mark. 4 factorial by definition is 4 times 3 times 2 times 1. N factorial by definition is n, and n has to be an integer, and it could be a 0, it could be a positive integer, 1, 2, 3, and so on. So the definition of n factorial is n factorial times n minus 1 times n minus 2, and we go down until we reach 2 times 1, we stop. 1 factorial by definition is 1. Another definition that's very important in here, and we need to define it this way, is the 0 factorial. 0 factorial by definition is 1. Now, let's say we wanted to calculate 7 factorial divided by 4 factorial. So we define 7 factorial as a 7 times 6 times 5 times 4 times 3 times 2 times 1. And then dividing by 4 factorial at the end in here. But remember, 4 factorial is the same as this part is in the numerator. 4 times 3 times 2 times 1 is actually 4 factorial. So we can cancel 4 factorial from the top and the bottom, from the numerator and the denominator, and the answer would be 7 times 6 times 5. Now remember now, this is example is like we are selecting 4 items, excuse me, we are selecting 3 items from 7 items. And we wanted to have no repetitions, but we allow the order to be matter. So we will figure out later on that this will be a 7 times 6 times 5, because we can fill the first place with a 7 out of the 7, and then to allow the repetitions, the second place can be filled in with 6, and then the third place can be filled in with 5. So here is the permutation by definition. It is an ordered selection of objects. If there is a collection of n objects to choose from, we are selecting n. So the permutation of n factorial will be just n factorial. If we're selecting n out of n, it means that we will be muting n. So if I'm selecting 10 items out of 10 items, then the order matters. So we selected the first one in 10 ways, then the second one in 9 ways, the third one in 8 ways, and the fourth one in 7 ways. And then we go down until we reach 1 and we stop. So if I'm selecting n out of n, the number of possible ways of getting this one will be 10 factorial. But if we are dealing with 3 out of 7 and so on, then we will have 7 times 7, 7 times 6 times 5. Here is just give you an idea what do we mean by the order matters. Let's look at this one in here. For instance, we have a set in here that has A and B. And in order to permute them, there are two possibilities in here. You put so I'm selecting 2 out of 2 in here. So we have A and then followed by B, or B followed by A. And so it is actually 2 factorial, or 2 times 1, or 2. If I'm selecting 3 items out of 3 items, so the number of permutations of ABC would be 6. And you can see here are the selections of 6. And it is a permutation of 3. Means it is a 3 factorial, means it is a 3 times 2 times 1. But remember, now we're selecting n out of n. And so on. And you can look at the same idea when you have 4 out of 4. Now, if we are looking into what we have in here is the same as this graph is showing me in here. If I am selecting 4 out of 4, the first place can be filled out with 4, and then 3, and then 2, and then 1. And the order matters in here. This example in here showing the race, and the first place matters. Who gets the first place? Or who gets the second place, or who gets the third place. So I'm permuting in here 4 players into 4 ordered places, and so the order matters in here. If you get the first place, is not the same as if you get the second place, and so. So the theorem in here says we have the number of permutation of n objects when we selecting all of them is n factorial. Now we get into the R permutations, not n permutation, but R permutation. What does that mean? Is that we are not selecting all the items. We have n, and we selecting from them R. And R, of course, is an integer, n is an integer, R is less than or equal to an n. So here is an example. We have a set of 4 items, A, B, C, and D. And we wanted to select 3 items from this. So here are the possibilities. We can have A, B, and C, but the order matters. Or we can have A, B, and D, and the order matters. Or we can have A, C, and D, and the order matters. Or we can have B, and C, and D, and the order matters. And you can see in here that we have 6 plus 6 plus 6 plus 6 means it is equal to 24. How did we get 24? Well, if we look into this rule in here, it says the number of R permutations of a set of n objects written as B n choose R, or sometimes we write it as an NBR, it is equal to n factorial divided by the difference between n and R. N factorial divided by n minus R factorial. So in our example in there, when we have 4, will be a 4 factorial divided by 4 minus 3. 4 minus 3 is 1 factorial. So we have 4 factorial divided by 1 factorial will be equal to 4 times 3 times 2 times 1, which is equal to 24. So here is the rules that we use it for the permutations of choosing R out of n, where the order matters. For instance, one way, for instance, when you wanted to arrange some 3 students, selected 3 students from 6 to have them sit into 3 seats. So we have 6, and we wanted to put these 3. Now, if I put the first person, the first student in the first chair, for me, it is a different than in being in the second place and so on. Or suppose you wanted to select a committee of 3, but the order matters, 3 out of 6. And the order matters means that who gets the president of the committee, who gets the vice president, and who gets the secretary. So here the order matters. So here is an example where the order matters. And so how many committees can we select? A committee of 3 members out of 6 where each one of them has a different position in the committee, then it will be a 6 permute R, which will be a 6 factorial divided by 3 factorial. And we can calculate that. And it will be equal to 6 times 5 times 4. Now, here is a different scenario in here when we have the combination. A combination is an unordered selection of objects. So the order doesn't matter. Who comes first? Now, so suppose you're selecting 3 students, but there is no positions in there, just a committee of 3. And they are all have the same thing. It doesn't matter who is that. So there is no sitting in. We're putting 3 students in 3 seats out of 6. It doesn't matter which students sit in where, and so on. So how many ways do we do this? Here is an example of this. Suppose we have a set of A, B, and C, where are the combinations of 2. So we are selecting 2 of 3, and C can hear that the number of possible combination in here is A and B, A and C, and B and C. That's it. Why? Because it doesn't matter. You have A and B, they are different from each other. Who comes first, A or B? It doesn't matter. So it is actually a smaller number of possibilities in this case, because we removed the possibility of having the same A and B but in a different order, and so on. In this case, we will have a rule says, how do we do it? We have this combination rule. It says n choose r, and it is equal to n factorial divided by n minus r factorial, similar to what we had before with the permutation, but we divide also by r factorial. Sometimes we write it like this, n choose r. So if I wanted to do like the rule we had, the examples that we have a few minutes ago, when we had 3 choose 2, it will be a 3 here factorial, and it will be here 3 minus 2 will be 1 factorial, and then r in here will be a 2 factorial. And so we will have 3 factorial divided by 1 factorial times 2 factorial, and the answer will be equal to just the number 3. Here is another way to do this one. In here we are selecting 2 people out of 5, and so where the order does not matter, as we said in here, it is a committee members, but it doesn't matter who's choosing first, who is a president or vice president. There is no president or vice president. It's just a committee of 2 members. All right, all of them have, or the 2 of them have the same authority, let's say. So in this case, the order doesn't matter. So we have 5 people. We wanted to choose 2 of them. So these are the possibilities. You can look in here. We have 5 different people, and we are choosing the 2. How many ways can we do that? Will be a 5 choose 2, which is equal to 5 factorial divided by the difference between 5 and 2 will be 5 minus 2 factorial, which is 3 factorial, and then we have 2 factorial. Then we can write 5 factorial as 5 times 4 times 3 factorial divided by 3 factorial. 3 factorial cancel with 3 factorial, and then we ending up with 5 times 4 divided by 2 equal to 10 ways. And these are the 10 possible committees of 2 members. All right. Here is another example in here. Suppose you're selecting 2 cards from a set of cards of 52 different cards. Then how many possible different cards can we have? And it will be a 52 choose 2, and we say choose C, 52 choose 2, or 52 C2, which is equal to 52 factorial divided by the difference. 50 minus 2 is 50 factorial times 2 factorial, and so on. Now let's apply also the multiplication rule in here with the combination. Let's say we are selecting 2 cards. Now, from the set of cards. Now, we wanted now an extra condition on the 2 cards. We wanted one of them to be of a certain type and the other card to be of a certain type. Let's say, for instance, the first type is the 12 picture cards. and the other card will be from the numbers, which are 40 cards with numbers on it. So what we can do in here is we look into a sequence of two tasks. The first sequence, the first one in the sequence is select the card from the numbers. So we have 4, it choose 1. And then we multiply by 12, it choose 1. So the answer would be a 40 times 12. Let's say we are not only selecting only 2. Now let's say we have a club that has 5 male and 6 female members, a total of 12. But we wanted to select a committee that has 3 men and 4 women. So what we're going to do now, we're going to do 2 tasks, and we do the multiplication rule. And we apply also the combination rule. The combination rule for each subtask. So the first task is select the 4 female out of the 7 female. And the order doesn't matter. Olivia and another person and another person and another person came in, but the order doesn't matter. So 7 choose 4 times 5 it choose 3. That will be the number of possible ways of selecting a committee of 7 from those 12 male and female. We have a similar problems in our textbook in chapter 3, and we will recommend that. I recommend that you go ahead and read some more examples in the book, and we discussed later in the book the use of these combination methods to perform another task. Later on, we defining what are the chances and then what are the probabilities of having this committee, for instance. And so we look into probabilities as multiplication, using the multiplication rule, using the permutation rule, and combination, and so on, depending on what is the situation is. Good luck to you guys, and read chapter 3. As I mentioned in my other presentation before, read chapter 3, read the examples a couple of times, see if you understand them, and then try the odd number problem. Try to solve them, because they have a solution at the end of the book. After you solve them, compare your answer to the answers given at the end of the book, and that gives you a confidence. And then you can try the homework problems and the assignment from the textbook, which would be including the even numbers. Remember now, the odd numbers and even numbers are similar. So if you do the odd numbers, you get some confidence by doing them and seeing your solution is correct. Then you guarantee that you will do a good job on the even numbers. Good luck, and I will stop here. Thank you so much for listening to me.